Okay, let's dive right into this. If you've spent, practically any time writing code, you've definitely bumped into arrays. They're literally the bedrock of computer science. But today, we're not just doing a quick glance at basic syntax. No, we're going to completely deconstruct them. We're taking a journey from the bare metal memory concepts all the way up to total algorithm mastery. So here's our level up syllabus for this explainer. 1. What actually is an array? 2. Static versus dynamic arrays. 3. Core array operations. 4. Searching and sorting. And finally, 5. The big O, reality check. All right, level 1, what is an array? Let's lay the absolute groundwork here. When we define an array, the absolute most important word you need to remember is contiguous. Picture walking down a typical high school hallway and just looking at a row of connected lockers. That is exactly, perfectly, how an array exists inside your computer's memory. It's not just scattered randomly all over the place, it's a single, unbroken block of storage. Every single item sits right next to the previous one, and they all hold the exact same type of data. Now, to actually speak the language of arrays, you gotta know 3 main terms. First, we've got the elements. And these are simply the items, the actual data you're stuffing inside those lockers. Next up is the index, which is basically how we address each locker. But, and this is a huge rule across almost all programming languages, indexing starts at 0. The first element is always at index 0, the second is at 1, and so on. And again, contiguous memory. That's the secret sauce that makes an array an array. It's that unbroken chain of data that lets your computer find things incredibly fast. Moving right along to level 2, static versus dynamic arrays. So here's a question for you. What happens when we build that row of lockers, but we actually have no idea how many we're going to need ahead of time? Well, that brings us to the great divide in data structures, static versus dynamic arrays. Static arrays are blindingly fast. The memory is allocated right on the stack, which is your computer's super fast short-term memory, right at compile time, giving you instantaneous access. But they are incredibly rigid. If you say it holds 5 elements, it holds 5 forever. Dynamic arrays, on the flip side, are allocated on the heap, a much larger, more flexible memory pool. They can grow, they can shrink. The catch? That flexibility brings along a slight performance overhead for managing all that memory. The way different programming languages handle this exact divide is actually brilliant. In languages like Java and C++, you have the power to choose. You can declare a strict, fixed-size static array, or you can use tools like Java's ArrayList or a C++ dynamic array using the new keyword to get that flexibility. But consider Python. Python lists are inherently dynamic right out of the box. You just create an empty list and start appending. The language handles all the resizing magic entirely behind the scenes. Which brings us to level 3, core array operations. Let's move from the underlying mechanics to how we actually interact with these things every day. You see, inserting an element into an array isn't always as simple as just dropping it in. Because of that contiguous memory rule we talked about, if you want to insert a new number right into the middle of an array while maintaining the order, you have to physically make room. Step 1, of course, is making sure you actually have the capacity. If you do, step 2 is where the heavy lifting happens. You have to physically shift every single element to the right of your target index 1 spot over. Only then, in step 3, can you finally drop your new value into that newly emptied slot. And then step 4, just update your total size. Now let's see how this logic applies when we want to do the exact opposite. Deleting an element is basically the reverse mechanical process. First, you verify the index is valid. Then, to close the gap you just created, you have to shift all the elements on the right 1 position to the left, essentially overwriting the item you wanted to delete. Then just update the total size. Now, here is a really cool pro tip. If the order of your array doesn't actually matter, there's a neat little trick. You can just swap the item you want to delete with the very last item in the array and then shrink the size variable by 1. Boom, no shifting required. All right, leveling up again. Level 4, searching and sorting elements. So now that we know the raw mechanics, how do we efficiently find things? You essentially have 2 main strategies. Linear search is kind of your brute force method. You start at index 0, and you just check every single element, 1 by 1, until you hit your target. It works, for sure, but it is slow. Binary search, though, beautifully efficient. It uses a divide and conquer strategy, where it checks the middle element and then literally cuts the search area in half, over and over again. But, and this is a massive but, binary search strictly requires the array to be sorted first. It flat out won't work on jumbled data. Let's take a look at the logic for finding the maximum and minimum elements in a Python list. Notice how the process starts by initializing the max and min variables using the very first element of the array. Then you just iterate, starting from the second element. In one single pass, you compare each number. If it's bigger than our current max, we update the max. If it's smaller than our current min, we update the min. It's incredibly efficient because we only have to walk through the array exactly one time.
And if you're wondering how this translates to strictly typed languages like Java and C++, it shows us something really interesting. The syntax is, obviously, a bit heavier than Python, but the underlying logic is perfectly identical. Both initialize with the first element, both start their loop at index 1, and both require exactly one pass through the data. It's just a perfect example of how algorithmic thinking transcends whatever specific programming language you happen to be using.
Now, what's really interesting about this next concept, array reversal, is how both Java and Python use a brilliant technique called the two-pointer trick. It's so smart. You set one pointer at the very beginning, index 0, and one at the very end. You swap the elements at those positions, then you step the start pointer forward and the end pointer backward, and swap again. You just keep doing this until the pointers meet right in the middle. It's an incredibly elegant, efficient way to reverse data right there in place. But what if we need to actually organize our jumbled data, say in ascending order? There are a ton of ways to sort, but bubble sort is one of the absolute most classic ones to learn. The mechanics are pretty simple. You just compare two adjacent elements. If the first one is larger than the second, you swap them. Then you move one spot to the right and do it all over again. By the end of your first full pass through the array, the heaviest, largest element will have literally bubbled all the way up to the very last index. And you just repeat this entire process until no more swaps are needed. And finally, we reach the boss level. Level 5, the Big O reality check. Look, everything we've discussed is great in theory, but we really need to know the real performance cost of these operations when we're dealing with massive data sets. So let's break down the actual costs. Think about access, Big O of 1. That is instantaneous. Because of contiguous memory, if you know the index, the computer jumps right to it. No searching required. But think about search, insertion, and deletion. They are all Big O of n, because as we learned, inserting or deleting requires shifting all those other elements around. If you insert an item at index 0 in an array of 1,000,000 items, you have to physically move 1,000,000 items. That is a massive performance cost. And when we evaluate the time complexity for sorting, well, the reality check hits pretty hard. Advanced algorithms like quicksort and merge sort operate at a highly efficient Big O of n log n in the average case. But think about our old friend bubble sort. It operates at a devastating Big O of n squared. That means if your array size multiplies by 10, the time it takes to bubble sort multiplies by 100. It's fantastic for learning the ropes, but absolutely terrible for actual large-scale production code. Which leaves us with one final, deeply provocative thought to end on. We know arrays are amazing for accessing data instantly, but we also just saw that inserting and deleting data is heavily penalized because of all that element shifting. So I leave you with this. If you're building a program that requires constant, lightning-fast insertion and deletion of data at totally random positions, what data structure would you be forced to choose over an array? I highly recommend you start researching links lists next to find out. Thank you so much for joining me on this deep dive, and I will see you on the next explainer.